What we're going to look at today, and by the way, we're still at the bottom layer of this architecture chart. We are actually understanding how data is stored and how indices are created and stored on disk. What we're going to look at today are multidimensional indices, okay, which is a special kind of an index that you use to create an index on more than one column inside a table. Why this is interesting? Well, most of the time you're actually coding queries that have several terms. For example, here, select star from or department equal to toy and salary greater than 50K. Okay? Now, this type of query is the most common query you would ever write in terms of the selects. In most cases, you're actually querying more than one column at the same time. And if you're querying more than one column at the same time and you would like to speed up that, you have an issue, because if you've created an index on a column but not on the second one, like for example creating an index on department and there is no index on salary, you need to understand that depending on the database engine might decide to use your index or it might not. And if it doesn't, then you're into trouble. Okay? And if it's not supporting multidimensional indices, you are also into trouble, because that means you'll have to create an index on each one of them and hope that the database engine will actually use them somehow. So for example here, if the database engine is not supporting multidimensional indices, then your best bet is to create an index on department and an index on salary and hope that the database engine is smart enough to be able to use both indices to answer this query instead of doing a linear scanning of the table, page by page, row by row, which is of an axis to answer this type of query. Okay, so the notion whether a database engine supports multidimensional indices or not is important, and this is one of the things you should look into a database engine when you're considering using one. Does it support multidimensional indices, or how does it support generally running such queries efficiently? Okay. So it doesn't have to support multidimensional indices, but it needs to be able to support running these queries that involve more than one term in an efficient way, perhaps by utilizing the indices you have on the individual columns and using them smartly to actually answer the query. So here is one strategy. Okay, if I ask you, okay, write your own database engine and try to support this type of query, what you would do? You probably tell me something like this, if I find from the metadata that the database programmer has created an index on department, I will go and fire a separate query, which is basically select star from where department equal to toy. Okay, which is one of the two parts or the two columns we were querying initially. So I'll basically try to use the index. So I will fire select star from a department equal to toy. I will run basically a query to find out all the rows where the department equal to toy using the index. So this is going to be log n if this is a b plus 3, okay? Or it's going to be of 1 if this is a linear or an extensible hash table. I will get all the rows where the department equal to toy, and then I will check using linear scanning all those rows that came in the result set for the salary greater than 25K. Okay? So basically, you use the index as much as you can. So that's a valid approach, and this is the least a database engine could do, which is to use, in the case of a query that has multiple terms, to try to use as much as possible the individual indices or the indices that exist on individual columns, and try to combine the output from using the index or coming out from the index data structure to answer the actual query that was posed to it. Because the other alternative would be to do linear scanning, brute force search on the whole table. Now here is a second strategy that a database engine could also decide to do. If you write select star from or department equal to toy and salary greater than 50K, and you have an index on department and an index on salary, then run this query as two separate queries. One on department alone and one on salary alone. You will get a result set from this data structure and a second result set from the other data structure. Basically a set of matching rows using the, say, the B plus 3 on department, and a set of matching rows using the B plus 3 on salary. Now what you do is you intersect the two result sets. Okay, so if in the first one it's returning that row number 1, 2, 5 and 10 are matching, where the department is equal to toy. So 1, 2, 5 and 10. And the other one is returning 1, 2, 6 and 9 are matching. So, which is salary greater than 50K. So you pick the intersection between the two, which is 1 and 2. Okay? That's again a smart choice a database engine would do, which is to try to make use of existing indices, even though the query is not directly going to this type of index. The query is really querying on two columns at the same time, using AND or 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 XOR or whatever. But as much as we can, if we can use an index, then use an index. Okay? I'm assuming here that the database engine does not support any type of multidimensional indices, and I'm referring here to multidimensional indices, which is going to be an index created on both columns at the same time. Like for example, here department and salary. So this would be one index where the input to that one index are two or more columns. Okay? So if the database engine does not support multidimensional indices, at least it should be able to make use of the existing indices. Now, this is something that some of you will actually think of, and that's why I've decided to include this, because it's an interesting, I would say, twist on indices, which is this notion of on-the-fly compound indices. Okay? Now, this is actually not really a bad idea, except has been proposed before many years back, and most multidimensional indices are trying to achieve what this will achieve without the problems that come along with this way of organization. So what is a compound, simple index here basically meaning? It means that you will create an index in which you interleave the values coming out from the two or more columns that you're building the index on in building the data structure. Okay? So here's an example of what I'm referring to. So here's an example of the interleaving I was referring to. So I got all the department values and I sort them. And then within every department I get the salaries and I sort them separately. So I've sorted all the salaries within the art department from 10 to 20K, 21K. Same thing for sales, same thing for toy, and so on. So this is called a compound index. Okay? Now this type of index has been proposed many years back and it has problems. Now the problem is related to what kind of queries you can answer with this type of index. Now if you're building this on department and salary and you get a query on department and salary, you will be able to answer this fairly well in terms of performance. Say you got select star from or department equal to art and salary equal to 17K. So you look first up using the art value and you find the reference to the page that has list of salaries, and then you look up that for 17K and you're done. Let's say also you got a query that goes on select star from or department equal to art, and there is no specification for salary. Now this type of query actually is called a partial query. Now a partial query is a query that is fired against a multidimensional index, but it does not have values for all the dimensions used to create the index, like select star from or department equal to art. And even that, for this specific query, it's okay. You're going to follow the reference beside the art and get all the salary, the entries there for all the salaries, pretty much for all the rows in the art department, or for all the people working in the art department, because that's their, you have one salary per individual, and you will include that in your result set. So even that, it's okay. You can still answer this type of partial query with your compound index. But the problem is, if you start to get query like select star from or salary equal to 15K. Now, you got 15K in art and you got 15K in sales, and perhaps you got 15K in toy. You will not know unless you load all the pages for the salary level. Okay? Now that makes this index not suitable for answering this type of partial query. The same thing for aggregate functions. Select star from minimum, or maximum, or count. You're going to load up all of these entries, okay? All of the second level pages here for the salary to be able to answer that. So one of the issues about multidimensional indices is what's the performance of the multidimensional index, and another thing is, can it answer partial queries or all types of partial queries efficiently as it can answer, the full query on the index, okay? So this will become an issue that always arises with multi-dimensional indices, because here's the thing. If you're writing queries that has more than one term, and you decide to speed up those queries using a multidimensional index, which is built on the columns that you are actually querying, like department and salary. And then later on, you also find that you need to write partial queries, which is queries that are involving only a subset of the columns that you're building the multidimensional index on. If the multidimensional index is not good in answering those partial queries, your performance will be good when you get a full query, but in the partial query it will degrade. So now you run into trouble, and if you try to fix it, if your multidimensional index choice was really bad in answering the partial queries, but was really good in answering the full queries, most likely what you will do is you will end up creating another single dimensional query like a B+3 or a hash, or a hash like a linear hash or extensible hash to answer the partial query, and you will hope that the database engine picks that when you run that query, that partial query, and it will pick the multidimensional index when you run the full query. So if you run select star from or department equal to so and so and salary equal to so and so, it will use the multidimensional index. And if you write, select star from or department equal to so and don't specify salary, or where salary equal to so and don't specify department, you'll cross your fingers and hope that it will use the other B+3 on department and the other B+3 on salary. Okay, so it complicates things if the multidimensional index is not good in answering partial queries. And it will become an issue like what is the database engine is doing internally with these indices, when it's using what. Now this is what I try to highlight here. What can we answer with this type of compound index? Department equal to sales and salary equal to 15K? Yeah, sure. Department equal to sales and salary greater than 50K? Yeah, sure. Department equal to sales? Yeah, sure. Salary equal to 15K? No. That's like a bad one, okay? That will end up you loading the whole index basically to be able to answer it. Now, how important are multidimensional indices? Now, to be honest, they were not that important before, okay? Because most of the time, people were quite happy with single dimensional indices like a B+3 on a single column, or a linear hash table, or a single column, and so on. But with the rise of geographic data, and we've already introduced, geographic information systems before in lecture 3. With the rise of geographical information systems, and with the rise of what's called spatial applications that make use of your location to give you a service, they became incredibly important. There is also another driving force behind the rise of multidimensional indices, which is the business community. Okay. A lot of the decisions made in companies are based on what's called business intelligence units, which are trying to analyze the data that the business is acquiring from the customers or from third parties to make better business decisions. And in many cases, the data is multidimensional. Okay, like for example, studying the consumer behavior of people who go to buy from Carrefour, in Maadi city center. Okay. You will study their demographics, their jobs, where they live, where they go to spend the free time. Do they do shopping on Fridays or after work? And you enter so many variables, and what you would like to do is to query those variables together. So basically, you're thinking of the data as multi-dimensional. It's not just a single dimension. Now, we really don't talk about this in this course. There's a whole spin-off from the database area called OLAP, or Online Analytical Processing, where they build something called hypercubes and so on, and they even have an extension to SQL language that supports querying multidimensional data. But what I'm giving you here are just the basics so you understand how you can create a multidimensional index, what multidimensional indices exist, and what's their use basically, okay? And what's the advantage and disadvantages of the popular ones. So all of these queries, which we have discussed before, were a major force behind the rise of multidimensional indices, okay? In fact, we have already looked at a multidimensional index, but I didn't tell you that it's a multidimensional index, which is the R trees, you know, because R trees are an extension of B plus trees, where in a B plus tree we store one value, while in R trees we ended up storing coordinates. So it became multidimensional, X and Y, or X, Y, and Z even, okay? Now, so answering all of those queries with a multidimensional index like R trees become extremely easy and simple compared to doing it without such a data structure. Okay, like which city is at this location, what is within 5 miles from so and so, what's the closest point to so and so. We've discussed this when we discussed spatial databases. But R trees is just one solution. We will see other stuff today that is related to that area, and that could be generalized, not just to spatial applications, but even to business intelligence, okay? So, for example, instead of saying what is within 5 miles from so-and-so, you could ask about the consumer behavior from this specific location, okay? Or from some shop, okay? So you could rephrase each of those questions to be, instead of asking about a location or location-oriented question, to be a business intelligence-oriented question. Okay? What we will look at today are 4 different multidimensional indices that are very popular in the database world, and many advanced database engines will implement at least one of them. Now, let's look at the first one. The first one is called the partitioned hash data structure, or generally most people would refer to as more of a mechanism rather than being a fully like a new or different data structure. The idea is like this: you would like to build an index on more than one column. Up till now, what you have learned in terms of working with hash-based mechanisms, whether the regular hash table or linear hash table or extensible hash table, we only had one column that we're building the index on. But let's say you have 2 columns you're trying to build the index on. How do you do that? Here's a very simple idea that will work great, okay? You got 2 keys from 2 different columns, and you hash each one of them. So you're going to get a hash value, h1 from hashing key 1 and h2 from hashing key 2. What you do is you translate it to binary. Again, this is a very popular idea in the hashing world. You translate each one of those into binary. And what you do next is you concatenate them together to make one big binary stream, okay, or one big binary value. And that's what you see here. Let me show an example of how this will work. So let's say I am building a partitioned hash table or a partitioned hash on index, let's call it a partitioned hash index, on 2 columns, department and salary, okay? So I retrieve all the values from the department, all the unique values from the department, and all the unique values from salary, and I will hash each one of them. So I only have 3 departments: toy, sales, and art. So I hash toy, get 0, hash sales got 1, hash art got 1, okay? Now, that's a decimal, I convert to binary, but obviously it's going to be the same here. Now, I do the same thing with salary. I hash 10k as a string, I will get out 0, 1. I hash 20k as a string, I will get, or as a value, as a number, I will get, 11, or sorry, 1, 1, okay? Which is 2. Or, sorry, which is 3, okay, which is 3. Now, when I hash 30k and I get 0, 1, and I hash 40k and I get 0, 0. Okay? Now, this is the content extracted from the table, what you see at the bottom. Fred toy 10k, Joe sales 10k, Sally art 30k, and so on. Okay? Now, I'm not showing you all the entries, I'm just showing you a sample of the rows that exist in the table, and I'm building this partitioned hash index using the content of the table. So the question is, what will go into the partitioned hash index? I've already hashed the values that appears in the department column and in the salary column. So what I'm going to do, I'm going to combine the output of the hashes, the binary bits, those bits, I will actually combine them. Okay, so when I look up a row, Fred, Toy, and 10K, if I would like to insert that in my hash, in my partitioned hash index, Toy is hashing to 0, 10K is hashing to 0, 1, so I'm gonna merge them together, becomes 0, 0, 1. Sales hashes to 1, 10K hashes to 0, 1, so that's going to be 1, 0, 1. Art hashes to 1, 30K hashes to 0, 1, so it's going to be 1, 0, 1. And these are the entries, that will be inserted in my partitioned hash index. Okay? Where am I getting this? Now, obviously, I'm using it symbolically here. It is Fred and Joe and Sally is not going to be inserted. What will be inserted is, for Fred, is going to be Toy and 10K. Okay? Or basically a pointer to where the row is in the page, in the table. Okay? That has Fred, Toy, and 10K. Okay? But I'm just representing it here symbolically with Fred, Joe, and Sally. Now, I'm showing you here more examples, as if I took the whole table and I grabbed row by row and I did a hashing of the department value and of the salary value, and I threw in a reference to that row inside my partitioned hash index. Now, when I get a full query like this, select star from employee where department equal to sales and salary equal to 40K. How do I use my partitioned hash index? I will go and grab the values, sales and 40K. I will hash sales, it's a 1. I will hash 40K, it's a 0, 0. So I should be looking in there, 1, 0, 0. Okay? As long as I follow the same rule in insertion in the search later on, then I will find it. Because when I was inserting Sally, I did the same thing. Sally was in sales and her salary was 40K. So I hashed before sales, it was 1, I hashed 40K, it was 0, so it's 1, 0, 0, and I put Sally there, or Sally's row reference, or the reference to Sally's row there. Okay? Now, so this is good, this is really good, this is OV1, okay, and on multidimensional. Pretty nice, okay? Obviously, there are caveats here. There are issues we have to be aware of. Let's say we get a partial query. Now the question is, can this answer partial queries? And the answer is yes. Select star from employee where salary equal to 30K. I will hash 30K. I will not need to hash the department because I don't have a value for the department, so I will not restrict myself. I will look everywhere for 30K. That means 001 and 101 apply. Both of them are candidate answers. And that's what you see here. I picked the row where 001 and 101. Why? Because 30K is given me 01. But the first bit, which is coming from department, I have no knowledge about it because it wasn't specified in my input query, because my input query is a partial query. Okay? So I've narrowed down my search a lot. You look up how many cells we have here. 1, 2, 3, 4, 5, 6, 7, 8. How many actually are we going to look in? We're going to look only inside 2 of them. Now inside those 2 we're going to do linear scanning, because I got to go to this page of the table and check the salary to make sure it's 30K. And this is now the next issue we need to discuss. What's the issue? I want you to look at the hashing of the salary values. Now if you noticed, 30K and 10K give me 01. Why? Because the hashing function is really input blind in terms of the relation between the input and the output. Okay? The hashing function is just a mathematical computation. So it just happens that I had collision. 30K gave me as an output 01 and 10K also gave me 01. So I ended up putting people with different salaries in the same slot if they work in the same department, because this means that 101 will have people with 30K and 10K, and 001 and 001 will also have people with different salaries by working in the same department, which is 0, which is toy, also falling in the same cell or colliding in the same cell. So because of that, whenever you grab one of those cells in the partitioned hash index, you don't include all the entries inside it. You have to scan the entries to find out which one matches your given initial condition, whether it's a full query or a partial query. Like here, for example, in salary equal to 30K, I know that. I need to look into 101 and 001. But it doesn't mean that my answer is all what's in there. I will scan what's in there to find out who has the salary of 30K. But still, this is pretty good, because I will end up looking into a fraction of the index and a fraction of the pages that exist in the table. So it's still O of 1. So what this is telling you is that a partitioned hash index can answer efficiently full queries and also partial queries. This is another example of that. Select star from employee where department equal to sales. So you hash sales, it's a 1. But you're not giving any information or any query about the salary. So what you're going to look for are people who ended up in the sales department, who ended up in all the entries that start with a 1. And this is what I'm referring to. All of these guys are candidates for the answer. They're not the answer, okay? But so you have to load the rows for Sally, Tom, Bill, and Andy and look up whether the department is equal to sales or not. And if it's equal to sales, you include it in the result set. Why? Because if you look again up in hashing the departments, sales and art are both colliding and giving you 1 as an output of the hash function. So you don't know which of these guys, Sally, Tom, Bill, and Andy, are in sales and which is in art, unless you actually do a linear scan of just these cells or these rows in the table or these employees to figure out what is their department. And this is again to clarify the idea that we're going to look up there for our actual result set. So partition hash, the pros over 1 axis plus some k checks on the entries in the same cell, obviously. Okay. Now it can answer partial queries, which is good. This is really good. Now the problem is it cannot answer nearest neighbor query. There is no notion of who's close to who. Okay, there is no notion of relation between the values of the columns. So if you think of the previous example, there's no relation between who works in which department or who has higher salary and at the same time. Okay, so it's you're just querying the values, but there is no relation between the values. Okay. The same thing for who's closer to whom, whose salary is closer to which salary, which if you try to translate it in the spatial world, if the department and salary were X and Y, and you're trying to figure out values that are closer together on the Y-axis, it has no meaning there, because in the first place, in any hashing mechanism, we don't have ordering of values. There is no notion of order, and consequently there is no order of proximity. So there's no meaning to ask about proximity. Now, by the way, what I describe here is an in-memory partitioned hash index. But if you implement this for real, you'll have to resort to linear hash table or extensible hash table to actually get it implemented. So I'm explaining here the high-level idea, but you will run into all trouble related to hash tables if you implement it as a simple hash table, which is going from n to 2n, and the sudden enlargement in the number of cells and so on, and the full reorganization that is required with the hash table and so on. So you still have to implement this idea as a linear hash table or as an extensible hash table. And this is why some people would describe this as just as a mechanism instead of being a completely new data structure, because it's an idea of combining values from more than one column into making one big bit stream, and the rest is just hashing. So you still need to go and solve the problem associated with traditional hashing or in-memory hashing, which we already discussed in lecture 4, which is linear and extensible hash table. So here's the takeaway. A partition hash mechanism enables the representation of several columns in the same hash table. That's really what it's all about. Let's move on to the next data structure that is used to create multidimensional indices. This is called a grid index. Okay? Now, the idea is quite simple. In fact, if I tell you to innovate and come up with your own multidimensional grid index, this is most likely what you will come up with. What this is a generalization of the idea of arrays. An array is single dimension. What's the generalization of a single dimension? 2 dimensions or n dimensions. Okay, where every dimension are used to store values from one of the columns you're trying to build the index on. Okay? So the intersection of the dimensions will tell you something. And this is really what this boils down to be. So as you see here, I have 2 dimensions only. If we code this as a Java, in Java or Python, this will be a 2D array, because I'm really building it here on just 2 columns. Now, in one dimension, I have values from the V column, and on the other dimension, I have values from the X column. Now, the intersection of a V row and an X column is going to be a cell that has references to all the rows that matches the particular V and the particular X we are trying to address. Okay? So this is the layout if you have a grid index on 2 columns. What if you have it on 3 columns? You can imagine this getting extended in the 3rd dimension, so it becomes like a cube. And then we can go and even create it in 4 dimensions, but we will not be able to visualize it. It's going to be like a 4D data structure or a 4D illustration, or 5D or 6D and so on. So the idea is generalizable to any number of columns, and visually it becomes obviously simpler to look at it as a table or a 2D column, 2D array. So this is what I'm going to show you. Okay? Now, just that we're on the same page here. The grid index is referring to everything that shows up here. There is the grid, which is often kept in memory, and there are the buckets or the pages which exist on disk. Okay? And then inside the buckets there are pointers to the pages of the table. So this is somewhat similar to, if you remember, the extensible hash table, where we had the directory and then the pages or the buckets, and from the buckets you go to the table. That's the same idea here. Okay? Now, so what you have inside each one of those cells in the grid, in the in-memory grid, is just a reference to a page. That is basically a bucket that has references to the different rows and the different pages in the table. Okay? Now, the good thing about grid indices, the idea is very simple. So we can quickly point out that you could answer full queries and you can answer partial queries quite efficiently. You can even answer ranges, which is not answerable. You cannot do with a partitioned hash index. Here you can answer ranges. So this is pretty powerful. Okay? Full queries are okay. Partial queries are okay. Ranges are okay. In fact, nearest neighbor is also okay, as you will find out. So that's why historically this was very, very popular, as an idea, and it got implemented in many incarnations in many database engines. Now, again, the dimensions of the grid are coming from the columns. What if the column values are not numeric? Well, you can assign them some numeric value, or you can put labels on every dimension to signify what does this stands for. For example, the first column in this grid is only for toy. for employees who are in the toy department. The second column in this grid is only for sales employees, and the third column in this grid is only for personnel employees, or employees in the personnel department. Similarly, the first row, not the first column, but the first row in this grid is for those who are actually between 0 and 20K. So if you intersect the first row with the first column, you get this cell that has a red dot in the corner, and that is going to be for those who work in the toy department and whose salary is between 0 and 20K. And if you look up the blue dot at the bottom right, that's going to be for the intersection of the last row and the last column is going to be for employees in the personnel department whose salary is greater than 50K. So you allocate the dimensions on you allocate the values on every dimension. And obviously they have to be mutually exclusive for this to work. They have to make some kind of a scale. So here is an example of a grid index with specific ranges allocated to every value or marker on each one of the dimensions. Why am I allocating ranges here? Because if you are having a column, like for example the X column or the V column, that has hundreds of values, you will end up creating a huge grid for no good reason. You're just going to be wasting too much space. And to avoid wasting that too much space, we could establish ranges for the values. Now we will talk about ranges later on because that will turn out to be a problem, but generally the strategy is we don't want to have an explosive size grid, so we will fall back to using ranges of values. So say that, just to show you how we would use this, I have established these ranges for X3, or basically, X1, X2, and X3 here are really going to be, I'm just using them as labels, but really what X3 will be is going to be 2 to 6. The label 2 to 6 that I have here, values between 2 and 6. And V1, V2, V3, V4 are going to be again missing or replaced by the ranges. So V4 will be replaced by the actual range, which is 100 to 250. Okay? Now, if I get up a query like this, select star from where X equal to 5 and V equal to 200. I will go to every one of the dimensions alone, like at the X dimension, and I will look for 5. For 5 will exist between 2 and 6, so it's going to be the last column. V is 200, so it exists between 100 and 250, so it's going to be in the last row. The intersection of the identified row and the identified column is going to be the cell that's highlighted here in red. I will go there and find the reference to the page on this that has references to the pages of the table. Okay? So this is how I actually use the grid index. Now about performance here, I will do binary search on the ranges in memory because the grid is actually in memory. The grid itself is in memory. And this 2D array I'm referring to. So that's going to be log n, and I'm going to do it twice on X and on V, so it's going to be 2 log n. So it's going to be log n, and then I load the red page, or the bucket that is highlighted in red here. That will involve some k processing of those entries, where k is much, much smaller than n. So I'm basically spending here log n plus k to actually find the addresses of the rows in the pages that I'm interested in. Okay? So this is how we do it. And this is an example, obviously, of a complete query, because I have a value for every dimension. What if you have a partial match query or partial queries? Like, for example, select star from where V is less than 100. So since I didn't get a value for the X dimension, I'm not going to isolate myself to any specific column. What I'm going to do is I'm going to work with all the rows where V was less than 100. So it's going to be basically the first 3 rows in my grid. Okay. So all the arrows that are coming out from the first 3 rows will be pointing to pages that I need to read, or buckets that I need to read, because these contain addresses of rows that I need to also consider. Okay, or it's basically part of my result set. All of them are part of are actually my result set. So as you see here, we can answer partial queries, and again quite efficiently, because we're going to isolate on the dimension we're interested in, or that is given to us in the query. We're going to isolate the rows we're going to work with, or the columns we're going to work with in log n, plus again some key processing. We can also answer range queries. So if I get select star from, or v is between 75 and 100 and x is greater than or equal to 4, that's easy for me. I will work with the v dimension to find where is 75 and 100, and that would be my row or rows of interest. And then the x is going to be the column or columns of interest. I intersect them, the row and the column. In this case, I will get this red circle, red highlighted cell. This will be my reference of interest. I will follow it to load the bucket that is highlighted in red, and that will actually be containing my pointers to the rows that will go into my result set. So here the performance is going to be 2 log n plus some key processing. Notice that in the partitioned hash index, we will not be able to answer such a query again. Okay, I already mentioned this, I'm stressing it because there's no notion of ordering, while here we're getting ordering in place. Okay, so we could use it to answer range queries. The nice thing about this is that we could also answer nearest neighbor queries. This is the first time you see a data structure, apart from R3s, that you actually get an ability to answer nearest neighbor queries. And again, don't think of this as just being geographic information. This could be used in the context of business intelligence, for example, to find out if, say, X and V are representing consumer home address and consumer spending pattern. Okay, so one of them is consuming a consumer address, and the other one is consumer weekly spending amounts. So even there, in that context, the nearest neighbor query makes sense. Okay, so if the cyan cell is for people who are in Maadi who spend more than 100,000 pounds, okay, the ones around it are going to be closer to it in that sense. Okay, but let's fix first on this notion of how you can actually get the nearest neighbor. Now, the query obviously is going to be if you think spatially, is going to be some kind of spatial query that tell me who are closer to me, given that my coordinates is 120 and say 4, okay? Or v equal to 120 and x greater than or equal to 3. So you look up first that location. So 120 is between 100 and 250, so it's the last row. X greater than or equal to 3 is going to be the last column, because the last column is for values between 2 and 6. So the intersection of the last row and the last column is the cell highlighted in cyan here. Okay? Now, this is where you're standing. This is where you want to find the nearest neighbor when you're standing there inside the cyan cell. So the nearest neighbor are going to be the 3 cells highlighted in red. Can you get them? Yeah, it's super easy here. Why? Because the arrangement is what's called an ordinal arrangement, which means it's ordered arrangement. X1 comes, then after it X2, then after it X3. So if we were talking about ranges here, if X3 is between 2 and 6, X2 is going to be between, say, -1 to 2, and then X1 is going to be -5 to, say, -1. Okay, so they are ordered in values on the scale. Okay? And you gotta get it this way so that you can do binary search in memory for the values. So they have to be ordered from smallest to largest on every dimension. So what that means, if you stand inside the cyan cell, the ones that are closer to you are going to be in the surrounding cells. And since this is in the corner, you only have 3 surrounding cells. So you go and load the references that are pointing to every one of those surrounding cells, grab the rows, and then you have to establish some kind of measure, like how would you say who are the closest to me, okay? Because there could be many points in those 3 cells. And here in this example, there is only one arrow in the cell above the cyan cell. So you go and load that bucket highlighted in red, and that will take you to some rows that has references to some rows in the table. And when you get those rows, you got to figure out how to compute from those rows only to the value inside the cyan, who is closest, if you want the nearest neighbor, the nearest one, okay? So if this is geometric distances, you could use something like Euclidean measurement to find out the distance between where you are inside the cyan and the distance to every other point coming from the table, from the red bucket here, or the bucket highlighted in red. So what I have been describing up till now is how we search in the grid index. The insertion is just following the same logic, because in order to find it using the algorithm we have been describing, which is looking up in every one of the dimensions for the specific range or value that we focus on and discard the rest, like focusing on x2 and discarding x1 and x3, or focusing on v3 and discarding v1, v2, and v4. In order to find it, it has to be in the right location, and the insertion consequently has to use the same algorithm that I have been describing to identify the bucket that the new entry needs to be inserted in. Now remember, again, this is the index, this is not the table. So we will start by inserting the new row as a result of the insert SQL statement. We will insert the new row in the right page, in the right table, and then we will keep track of where is that page on this, which row in that page did we do the insertion in, and then we will come here and use the same algorithm that I have been describing to identify which one of the X's and which one of the V's that we need to track, and consequently the intersection of the X and the V will give you a specific cell, a specific reference that you go to, a specific bucket basically, that you will put in the key that you just inserted, and in the row, I mean as part of the row, and the reference to where that row is. Okay, so basically in order for the search to work, you have to use the same logic in the insertion, and in order for the deletion to to happen, you still have to find the right bucket. So again, you follow the same logic. Now, what's the issue with the grid index? If this is such a great data structure, why do we have anything else? This is working in 2 log n plus some k processing. In fact, I would even modify my performance analysis here to say it's not going to be exactly 2 log n. It's going to be some 2 log m plus some k processing, because if we work with ranges, the number of ranges are going to be much smaller than the number of entries. For example, if I have 1 million entries in my table and I'm creating ranges, I could perhaps create 500 ranges. So X will have 500 labels from X1 to X500. Each one is a range. So I will describe that as M instead of actually N. And the same thing for the other dimension, the V. So it sounds like a very good actually data structure, a secondary storage data structure that we could use to support multidimensional queries. It will enable us to do exact value queries, it will enable us to do partial queries, it will enable us to find range queries or find answers to range queries. It will also enable us to find nearest neighbor queries. So what better to we can do than this? I mean, it sounds like a very interesting data structure in terms of its capabilities and in terms of its performance. It's O of log m, if you like, plus some k processing of the entries in the bucket. So what's the problem then? Why did people invent other multidimensional indices and not just get used to using grid index, since it sounds like it's going to solve all our problems? And here is the caveat, here is the issue, here's the big issue with grid indices. Everything we have mentioned up to now is good, but there is one really, really complicated aspect about it that makes it almost unusable, except in one case. What's the issue? The issue is related to the ranges. Those ranges are hard to find. What do I mean by that? Let's say you get a table that has 100 rows and the values span from 1 to 100. What are the good ranges? Now you tell me, okay, I will pick 10 values for x, from x1 to x10, and x1 will be from 1 to 10, x2 will be from 11 to 20, x3 will be from 21 to 30, x4 will be from 31 to 40, and it goes like this. So you're basically dividing it into equal ranges, where in every range there are 10 values or 10 possible numbers. But if I tell you later on, well, but you've got 100 rows and the values range from 1 to 100, but you have duplicates, and although the values range from 1 to 100, it goes like this: 1, and then 50, and then 50, and then 51, and then 51, and then 52, and then 52, and this goes on all the way till the 100. So the 100 values are actually clustered in the second half of the 100. Okay? They're not evenly distributed. So your pick is not good. What you should have picked is 1 to 50 as a range, and then 50 to 60, and then 60 to 70, and 70 to 80, and so on. Or even perhaps 50 to 55, 55 to 60, 60 to 65, and so on. Okay? So the good selection of a range for a particular value on any one of these axes we have in our dimensions is dependent on the data we have. Okay? We cannot just keep track of the minimum and the maximum and divide equally the range between the minimum and the maximum into smaller sub-ranges, because this way we are assuming that the data is evenly distributed, that we are going to get an approximately equal number of points within every one of our ranges, and that's not necessarily true. So in this slide, what I'm showing you is the impact of the range selection. If you pick your ranges after carefully considering the values that are stored in the column you are using in every one of the 2 dimensions in the case of a 2D grid, if you pick it accurately, in the sense that you're picking it to divide the data among possibly all the buckets that you could have, what you'll end up with is a small portion of the data or of the values in that column appearing in every one of the buckets. So you have a nice distribution of all the values over all the buckets, and consequently you will get the log m plus k that we were discussing. But if you just pick it blindly, what you could end up doing is accumulating all the keys from the column you are building the index on into one bucket. And since the bucket is going to get full, you're going to link to it other overflow buckets, and link to the overflow buckets and other overflow buckets. So when you search, you're always going to the same cell in the grid, which in the case on the right side, it's the intersection of x1 and y2. Okay? You'll always go to the same cell, and you will always go and search linearly in the bucket and its linked overflow buckets, which is O of n performance. It's not even O of m, it's O of n performance. Okay? So there's a big difference in terms of performance based on the ranges that you select and you use in each one of the dimensions. But you will not be able to actually find that range unless you inspect the data. And here is the big problem: the data will change. So every time or every once in a while, once you realize that the data has changed significantly, the values has changed significantly, you have to go and reorganize your grid. In other words, use different ranges and consequently move all the entries between the buckets. And obviously this is harder. You don't want to do that. This is way too expensive. Okay? So let's say x1 was, the range was from 1 to 10. Because of a sequence of inserts, updates, and deletes. Now you don't need it to be from 1 to 10, you need it to be from 1 to 3 and move the rest to the next, x2, merge it with the range of x2. So let's say it was from 1 to 10, 11 to 20. Now after a bunch of changes to the data, after the data changes, you want to make it from 1 to 3 to have even distribution of values in, across all buckets. You want to make it from 1 to 3 and from 4 to 20. What that means is you have to load these pages and move the entries between the buckets. Okay? So that's obviously an expensive operation. And if the data keeps changing and you keep doing that, you spend most of the time changing the values around between the buckets on disk, between the pages on disk, which is excessive I/O. Okay? So obviously this is a very serious problem. Even if we are able to find the correct ranges for a given data set, for a given snapshot of a table, once the data changes, your ranges are not valid anymore. Once you get clustering, which is what you see on the right side here, you run into trouble. You're going back to O of n. And this is really the big problem with grid indices. Now this problem is actually is not just for grid indices. This has to do with a class of problems in graph theory called graph partitioning. For example, here, if you look at this map of points, okay, if x and y are basically coordinates, okay, and these dots represent villages or cities, and you would like to divide them into municipalities, basically administrative divisions, so you have approximately the same number of villages in every administrative division. So you would like to find the lines that gives you rectangles or squares, where in every rectangle or square there is approximately the same number of villages, kind of for fairness, to be able to provide services equally to all the villages. Okay. Now this is not a trivial problem. Is it solvable? Yes, but it's not trivial. Okay. In the case of a map, it's actually much simpler than the grid index because the villages' locations are not going to change. But in the case of the grid index, the values are going to change. So as if it's on this map, the points are moving, the villages are moving. Okay. So once you calculate it, if they move, you have to recalculate it again. Okay. So we humans, if I ask you to do this as an exercise, you will be able to do it because we can eyeball it and we can kind of do it by trial and error until we get the correct divisions. It's going to be something like this. Okay? But the problem is with computers, we will have to rely on an algorithmic design technique called dynamic programming, which you learn about in CSAN 703 in the analysis and design of algorithms course. And this problem is solvable, by the way. It's an example of what's called an optimization problem, where you're optimizing between two choices, the choices on the dimensions, basically, that you have in the grid. But it is computationally non-trivial, depending on the algorithm you're going to use, the DP algorithm you're going to use. There are a number of algorithms you could use, but all of them are computationally non-trivial. And if the database, and this is really the nature of the database, is changing all the time, the table content is changing all the time, that means you will run this algorithm over and over and over again, which doesn't make sense. Okay? Now, so to summarize, grid files, they are good for multidimensional searches. They will give you the nice O of log m plus k. Again, m here is the number of ranges you establish from the data, from the n data points. Okay? The problem is that the grid has to stay in memory. So what that means, you will try to make it as small as possible, and this actually again complicates for you the range selection, and you still have the problem of range selection. Okay? Here is the takeaway. A grid index efficiently supports exact value, partial, range, and nearest neighbor queries. However, creating and updating the ranges used is inefficient. Okay, and this is really the important point, this makes grid index most useful in cases when the majority of data is inserted first into the table we are building an index on, and next the index is created and queried. In other words, when would you use a grid index? So if this is the question, when would you use a grid index? You would use a grid index if you will upload all the data up front, you run an algorithm to find the good ranges, and then you keep firing queries against this data. Well, is this something that is realistic? Well, in most database cases, actually no, except if you're actually collecting the data up front. Perhaps, the example that would come to my mind is in the case of doing, kind of business intelligence reporting, in the sense that you collect information about consumer behavior and you upload it into the database, and then you keep firing queries against the collected data, and that data will not change until you go and recollect the data again, and consequently you need to build your ranges again. Okay, so if you can upload the data first and the data is fixed, you're not going to change it. So this is not about a live database. This is not about a database, for example, or should not be used in the case of a database behind an e-commerce website where the data is changing all the time. But if you're collecting data as a side activity, okay, from various sources, regardless of how you collect it, and then you upload it to the database, and then you're going to fire lots and lots of queries trying to understand the data, or generate reports from the data, or find new patterns for business intelligence purposes and so on. Yeah, sure, go ahead and use a grid index, because you're going to build the ranges once and keep using them. The next data structure we're going to look at that is used also as an indexing data structure in some databases is the KD tree. Okay, KD trees are an example of binary trees. So at most, every node in the tree will have two children, left and right. And KD is called KD for K dimensions. So it is actually a multidimensional data structure. It is used to query or answer queries on multidimensional data. Okay? Now, just like all the indices we have seen, you have to point to the pages of the table, and that will be the case at the bottom of the KD tree, just like at the bottom of the B+ tree, you point to the pages of the table. This is an example of a KD tree. The idea is very simple. We're going to alternate the dimensions on the levels. We could have as many dimensions as we like. What you're seeing here in this example is a KD tree built on two columns from some table, the salary column and the age column. If you notice, I start here the root with the salary. I could start level 0, the root level, with any of the two dimensions, salary or age. So I decided to start with salary. Since I have started with salary, the next level in the tree must be for the age information. Now, the one after it must be for the salary, and the one after that must be for the age. So the alternation here is going on like this. Starting from the root, it's salary, then age, then salary, then age, then salary, then age, then salary, then age, and so on. If I had a KD tree built on 3 columns, X, Y, and Z, I could pick any one of the columns to start with. But once I pick that, and once I pick the next one, I'm fixed with the order. So if I pick X first, Y next for level 2 in the tree, where level 1 is the root, then it's going to be X, Y, Z, X, Y, Z, X, Y, Z, X, Y, Z. I keep alternating the dimensions. I do not pick a dimension 2 times in a row. So this is the first idea you need to understand about KD trees. Okay, it's the alternation of dimensions on the levels of the tree. The second thing you need to understand is that this is very much like a binary search tree, but it's applied level at a time. What does that mean? In the binary search tree, we have this invariant that all nodes to the left, or all values to the left, has to be less than the parent, and all values to the right has to be greater than or equal to the parent. So let's look at this KD tree. At the root level, I decided to start with salary, and I have salary 150. Applying the binary search tree invariant, what this means that all salaries to the left of this node that will come anywhere in the tree later on to the left side will be less than 150. All salaries that are greater than or equal to 150 will go to the right. Now let's go to the next level. I have age 60 and age 47. I didn't tell you yet how all of these are inserted, but I'm telling you here that how we apply the binary search tree invariant. So age 60, this means that all ages that will come to the left of age 60 has to be less than age 60. And all ages that are greater than age 60 will come to the right when I'm standing at age 60 node. Okay? Now, let's try to combine our understanding of this invariant for two levels, salary 150 and age 60. If I go left from salary 150, this means the salary is less than 150. If I go right from, after going left, I go right at, the right of age 60, that means I am working with values where the salary, or rows where the salary is less than 150 and the age is greater than 60 or equal to 60. Okay? If I went left, starting from the root, I go left, so that is salary 150, left means less than 150. And if I go left of age of 60, so age is less than 60. So now I'm standing at age less than 60 and salary less than 150. Okay, so we are applying here the binary search tree invariant, but we're applying it level at a time. Now, if you look here, there are two types of nodes in this tree. There are the oval nodes, which are the nodes that will be in memory, and this represents the particular value from the particular dimension we have in that specific level. And then we have these rectangles or squares that actually are the pages that are in disk. So what you see actually inside any one of those pages is the values in the specific row that we are storing there. So for example, if you go left and then right, you will see a page that has 70, 1 and 110, 85 and 140. Now, the first is age and the second is the salary. So 70, 110, that's someone whose age is 70 and whose salary is 110. If you think of these values in terms of the traversal of the KD tree, we went left, so salary is less than 150. Indeed, the salary is 110. And we went right from age 60, and indeed the age is 70. So that is actually the right location for it. The same thing for 85 and 140. 85, it's to the right of age 60 because 85 is greater than 60 as an age. And 140 is less than 150. That's why it went in that page. Okay? So when I'm inserting any value, any new row, basically, I need to know at every level what I'm working with, which dimension I'm working with, okay? And I decide to go left or right, comparing the entry in the row with the specific value that exists in the node in the tree, okay? So when I was inserting 70, 110, I looked at the root node and it says salary, so I will look into the salary value and it was 110. 110 is less than 150, so I go left. And then I look at the next node and it says age and the value is 60 and the age that was given to me in that row is 70, so I will go right. And this is why 70, 110 went into that page. Okay? Now, what you see here is the construction of this KD tree after I have inserted several rows. So it starts from an empty tree when the table is empty, and once actually you start inserting rows, you insert the row in the page of the table, and then you come and you insert an entry here in the index in the specific page on disk, and you have a reference which is currently missing, from this chart. As always, it just complicates the slides for me, so I omit them and I mention them in the explanation that it's not just 70, 110. There will be a reference, an address of where is that row that has 70 and 110. Where is that row in the table? Which page and which row in that page? Okay, so that is not really visible here. So the information is missing the rows that goes to the pages of the table. Sorry, it's missing the arrows that goes to the pages of the table, not the rows. It's missing the arrows that goes to the pages of the table. That tells me where is this row that has age 70 and salary 110. Okay, there will be other obviously columns that or values for other columns in this table according to the table schema. Okay. So let me show you an example of, how do we search in the KD tree. I hope now, given my explanation, this is clear. If you get select star from where age equal to 50 and salary equal to 100, and if you happen to create a KD tree on age and salary, and that's what you have now, what you're going to do is you want to basically reach to one of those pages at the bottom of the tree, okay? Because there will be the reference to the row or the rows that answers your query. So you start by looking inside the node again, salary, and it says salary was 150 and you're looking for 100, so you go left. Now you have to look inside the node to figure out what dimension it represents, and it represents age, and you're asking for age equal to 50, and this is age 60, so you go left. Now it says salary 80 and you're looking for salary 100, so go right. So as you see here, that a node could have at most 2 children, and those children could either be another node or a pointer to a page on disk. Okay? Now, you load that page and you look for 50 and 100 and you find it and you return it in the result set, which is basically you grab the reference beside 50, 100, you go and load that page of the table that has this row and you include that row in your result set. Let's work out an insert in order to understand how this is really built. So I'm inserting here age 35 and salary 280. Now, I start with the root is for salary, 280 is greater than 150, so I go to the right. Now, I'm working now at the age, and what I'm interested in to insert is age 35, and this is telling me age 47, so I go to the left. Now I'm working again with salary, and I'm looking for, to insert salary 280, and my salary is 300, so I go to the left. And I follow this left pointer and I find there is actually a page. I load it from disk, and inside it there is an empty space, so I put the 335 280 inside the page and put it back on disk. And that will be the final picture. Now let's do another one in order to see things a little bit clearer when it comes to creating those pages. I'm inserting now 35 and 500. 500 as a salary is greater than 150, I go to the right. 35 is less than 47, I go to the left. 500 is greater than 300, I go and load this page following the reference, and to my surprise, or perhaps not, I am finding a full page. I'm here again assuming a trivial case where I have only 2 entries per page. I'm doing it that way to show you how actually this tree is constructed and how those pages and levels are actually created. But obviously in real scenario, you won't have 2 entries, you will have hundreds of entries. Now, the question is what to do now. Now the page is full. I cannot insert 35 and 500. There's no way I can do that. But I need to insert. So what I'm going to do is, I will create a new page to be able to insert. Now, here is the problem. If I create a new page, who's going to point to it? How can I link it to the tree? I cannot, because if you look now, salary 300 already has 2 children. Those 2 pages, the one that has 30 and 260, and the one that has 25, 400, 45, 30, 350. So I simply cannot, insert a page and try to link it. Creating a new page is easy, but how do I link it to the tree? The only solution is to create a new level a new alteration of dimensions in the tree. I was lastly working with salary, so the next level to be created is going to be for age, and that's what I'm going to do. That's what you see here on the tree on the right. I was working with salary 300, and since I found that the page is full, I am now going to create a new node or a new level. A new level will give me 2 more pointers, okay, left and right. Since I was working with salary, now the new level has to be for age, okay? The next question is going to be what value will go in there, okay? Now, what you're seeing actually here is a simple choice. I am going to list the values sorted for the age dimension for all the entries that I have in those 2 pages, the new one and the old one, okay? Remember, I'm inserting 35 and 500, and I already had 25 400 and 45 350. So I will list them in order. It becomes 25 35 45. I will pick the number in the middle, and I will make the age, is representing age 35. Why am I doing the number in the middle? Because I would like to have an almost even split of the rows that I have between the old page that existed, that was full, and the new pages that was just created. Okay? Again, think of the more realistic scenario. I probably have in a single page here in a KD tree between, I would say, 5 to 600. If you would like me to be accurate, well, we have to understand that this is based on the cylinder size. So if the cylinder is 64 kilobytes, we are most likely having something like 256 at least entries. So now when I create a new page, I would like to have a nice split of 128 and 128 entries on every one of the two pages, the old and the new. To get this split, what I could do is I could actually pick the number in the middle, and that will give me this kind of split. And that's what you see here, more or less. The 25 and 400 went to the left, and because of the invariant, it has to be less than, so 25 is less than 35, and the other two, 35 and 45, went to the right. Okay, this is, by the way, is not the only way we can do this. There is actually a number of ways described in your textbook, and even in previous exams, and I used to explain other techniques, but due to the kind of my attempt to save time to cover other material, I removed those slides. But I can tell you, right away that researchers have tried or experimented with, or there are some actually implementations of KD trees that don't do what I'm describing here. In fact, they will calculate the weighted average of the entries, 25, 35, or 45. This actually makes a lot of sense when you have lots of duplicates. Or they could do all kind of other things. Okay, so you could calculate the average, you calculate the weighted average, you can just pick the number in the middle, okay, or you can even pick the median and so on. Okay, so there's a number, so median, mode, mean, all are valid approaches. Okay, now the point is we're trying to actually create a split between the two pages, the old and the new, in terms of the number of entries that exist in every page. So, what are the pros of KD trees? The nice thing is it's log n. Okay, the number of nodes that you typically have, not the pages, but the nodes, will always be very small. It's going to be log n. So most likely you can fit it in memory. This is very interesting because that means you can answer multi-dimensional queries in log n, and you're guaranteed to not run into trouble like the ones we have seen with grid indices, okay, or even other data structures where you're not able to fit in memory what you're working with. Well, here obviously this is not going to be an issue at all. Okay, now because it's log n access, and it's also log n memory space. Now what's the problem? The problem is this is only usable in the case of exact value queries, where you have a value for every one of the dimensions. Partial queries will require you to traverse the whole tree, so you will regress to O of n. And nearest neighbor queries, again, is not supported in any way here, because according to how the data is structured here, the data is kind of split evenly, and you don't consider proximity. So again here, this is not the proper data structure to use if you're interested in nearest neighbor queries, or if you are having partial queries where some of the dimensions are not mentioned. Okay, so the tree that we were looking at was built on salary and age. You need a value for salary and a value for age to be able to get the log n performance. So you go down at every level, and you have something to work with. But if you have a missing dimension, like no value for age, you will have to traverse both sides of the tree after selecting the salary. Okay, so this is the KD tree. My takeaway here is that a KD tree index efficiently supports exact value queries. It is inefficient in answering range queries and partial queries. Its greatest advantage is that it has a small memory footprint compared to other multidimensional indices. Okay. So who uses KD trees? Well, actually, PostgreSQL is one of the databases I know that uses KD trees. I have put for you here a link to a documentation of PostgreSQL. And they refer explicitly to KD trees being one of the two supported indices for multidimensional data, specifically in the case of spatial data. So it is actually included as part of what's called the gist library, which is a library within PostgreSQL. It's a plugin library that gets loaded into PostgreSQL when you download it. So it's really part of the database engine. And the KD tree is created automatically. You don't explicitly create it. All what you do is you say create index on this table using, and you specify the columns that you're going to use to create the KD tree, and you just call the gist function, which is highlighted in red here. Now, this is a bit of a simplified syntax, because for real, actually, if you're doing it, beside column 1, beside the column name, you will pass a structure that has some configuration information for gist. So I'm not really here, showing it, because it's kind of an implementation detail. But ultimately, you will pass something in this structure that says, like, use a KD tree, and ultimately, you get a KD tree created for you. And from now on, if you fire a query on this specific table, on column 1 and column 2, it is guaranteed that you will be running the query through the KD tree, or basically answering the query through the KD tree that's maintained internally inside GIST. Now, the next index we're going to look at is called the bitmap index. This is a very, very popular index in the database world. Okay, in fact, this is probably the second most popular one after B+3s. Okay, and it is incredibly simple, to the point that you won't believe how simple it is. Okay, so here is the idea. This is called the bitmap index. So obviously, we're working here with a bitmap, and I'm sure you have learned what a bitmap is from your media courses. Okay, so it's basically a listing of bits. That's as simple as this is. Okay, now what we're going to do is we are going to keep a bitmap, or a listing of bits, for every value we have in a column. As much as this sounds crazy, this turns out to be actually quite efficient and quite useful. So let's see an example of what I'm describing here. This is my example here. Let's say I have two columns, F and G, and these are the values inside these two columns. Obviously, these two columns come from some database table. Okay, so how many rows I have here? I have 1, 2, 3, 4, 5, 6. 6 rows in this table. And I'm building a bitmap index on F and G columns. So what that means, I will scan all of F and get all the values there, and I will create a bitmap for every value that appears there, every unique value. So I have 3 30s, but I'm just going to build a bitmap for 30. And I have 2 40s, I'm going to build a bitmap for 40. And I have a 50, I'm going to build a bitmap for that. That's what you see on the right side. Now, what's inside the bitmap, which is the sequence of bits? I will put a 1 every time 30 appears. So I'm assuming here I'm going to number the rows from top to bottom, and row number 1 has a 30, so I put a 1 there. Row number 2 has a 30, so I put a 1 beside it. Row number 3 has no 30, it has a 40, so I put a 0. Row number 4 has a 50, so I put a 0, it's not a 30. Row number 5 has a 40, so I put a 0, and the last row has a 30, so I put a 1. So the bitmap for 30 is 110001. This is how simple and naive this is. Okay. Now for 40, I'm going to build a similar bitmap, so it's going to be 0, 0, because I have 30s there, there is no 40, and then a 1, because I just seen a 40, and then 0, then 1, because for the second 40, and then a 0. The 50 is going to be 0, 0, 0, 1, 0, 0. Okay? 0, 0, 0, because I have in the first 3 columns 30, 30, and 40, so it's not a 50. And once the 50 appears, I put a 1, and then 0, 0, because I have 40 and 30. And I do the same thing for the G. Okay, I have built a bitmap for foo. So foo appears in the first row and in the 4th row, and that's it. So it's going to be 1, 0, 0, 1, 0, 0. bar is going to be 0, 1, 0, 0, 1, 0 because it appears in the second row and in the row before last, and baz appears in the third row and in the last row, so it is 0, 0, 1, 0, 0, 1. Now I'm sure by now you're telling me this is as stupid as it can ever get, because these bitmaps are going to be huge in length if you have a huge table, and I already mentioned before that we always think of the case where we have hundreds of millions of rows, gigabytes and gigabytes of data, okay? And now you're going to go and fetch every value, and for every unique value you're going to create a bitmap that has perhaps 100 million bits, okay? I'm sure you're thinking of that, and I'm telling you yes. The answer is yes. That's what we're going to do. And the question is, like, how come this can be in any way efficient? Well, before we actually address this, let's see why this is interesting. Okay, this is why this is interesting. What can I answer with these bitmaps? Well, if I get select star from where f equal to 30 and g equal to 4, can I answer it? Yes. I will grab the bitmap for 30, grab the bitmap for 4, and what am I going to do? If the query select star from or f equal to 30 and g equal to 4, since it's an AND, what I'm going to do is I'm going to AND, bitwise AND, the bitmap for 30 and the bitmap for 4. So this is something interesting. We haven't seen anything similar to this before, okay? What if the query select star from where f equal to 30 or g equal to 4? I'm going to do a bitwise OR. Very interesting as well, okay? Now, what if the query is select star from where f equal to 30? Yeah, sure, I'm going to grab the bitmap for 30, and here's my answer. So what this means, bitmap indices can actually answer exact value queries, ANDed or ORed. They could answer also partial queries on one of the columns, and the other one we will not have a value for. That's very interesting, okay? Now I'll tell you what's really interesting here. If we are doing an AND or an OR in the exact value case, we are actually doing bitwise operations. Why this is interesting? Because, well, first of all, we have never seen this before in any of the indices we studied. And bitwise operations are particularly interesting because they are the fastest operations you can do inside the CPU. There's nothing faster. You are basically, as they say, exercising the wires, exercising the circuit. You're switching on and off the binary, circuit inside your CPU. So in terms of speed, you can't go faster. You just cannot go faster. There's nothing faster than the electronics itself, the circuits itself. Okay, the NANDs and the NAND circuits you have in your inside your CPU. The transistors themselves. So bitwise operations are the fastest you could ever execute, and this is getting employed here right away. If we have an AND in a SQL statement, it's going to be bitwise AND. If we have an OR, it's going to be bitwise OR. In fact, any kind of bitwise operations you could make use of, we will make use of by mapping from the SQL, the high-level fourth generation language, to directly to the bits. Okay, and this is why this is interesting. Now, let's actually think a little bit more. Can we answer range queries? Okay, can I say select star from where f is less than 50? Well, if I have the entries sorted, I'm going to get all the bitmaps for all the values less than 50, and I'm just gonna AND them or OR them. Let me just give you a second to think. If I say select star from where f is less than 50, so I need 30 and I need 40. Either of them will be in my result set. So it's either I'm going to OR all the bits, okay, for 30 and 40. Okay, now that's provided that we can maintain this list of values 30, 40, 50 sorted. So we could kind of make use of it to actually answer even range queries. Okay, now, and we can also answer range queries on both in both dimensions at the same time. So it turns out actually to be quite a good idea, actually, if you think of it. We're doing bitwise operations and we're capable of doing a lot of stuff. Obviously here nearest neighbor query has no sense at all because there is no notion of proximity here in any way. It's just the data is just bitmapped. Okay, so we didn't do any kind of computation or any kind of representation of proximity, so this is not really in the game with us. But almost everything else sounds like we can do. Okay, and this is what I was just stressing on, that you can answer many query types, including on specific value and or XOR and range. Okay, and bitwise operations are super fast. That's why this is a very interesting indexing data structure. Now, let's discuss the problem with bitmap indices, which makes everyone, baffled by the index when you hear about it for the first time. The problem is the bit sequences are going to be ridiculously long. Okay, in fact, there are as many rows as as many rows as you have in the table, as many bits as you will have. So if you have a table that has 500 million rows, you will have for every one of the values a bitmap of 500 million bits. Okay? Yes, that's a problem, obviously. But here is the issue. Compression algorithms have been around for many years, and they have actually advanced tremendously. Okay? Because historically they belong to an area that even predates computer science, called information theory. And research in compression algorithms has been around since at least the early 1960s. So we have like lots and lots of compression techniques, and we know a lot about compression. And the status of compression techniques are so advanced that we can do a lot of tricks with the data to be able to manipulate it while it's still compressed. And that's exactly what happens in the case of bitmap indices, that the index itself is compressed. And you have actually learned before, at least in the media courses, some types of compression. In fact, we also, you're going to see that if you haven't seen it already later on in some media courses. So the point is, we can compress. Like for example, the simplest kind that comes to mind is run length encoding. Okay, so I could, instead of storing the bits, I could store information about the bits. If I have 50 zeros, I can write the number 50 and 0. So instead of occupying 50 spaces, I will occupy 3 spaces. Instead of the 50 zeros, I say 5, 0, 0. So it's 50 zeros, okay? Or 50 dash zeros. So there are lots of compression techniques that are used inside database engines when they decide to support bitmap indices because of the length of the bitmap. In fact, there are compression techniques that you could manipulate the compressed data while it's still compressed, or at least know about what's inside the compressed data without actually compressing it. So there's lots of interesting stuff here that is beyond the scope of this course, but the point I would like to communicate to you is that we will compress the bitmaps or inside the database engine if it supports bitmap indices. Don't be don't shy away from using it, because the data will be well compressed, and the bit stream will not be totally uncompressed unless you're writing some really ugly query. And in that case, actually, database engines are smart enough to avoid using a bitmap index. Okay, so that's a great news for us. Okay, because that means we could use bitmap indices as a multidimensional data structure, and it's also used as a single dimensional data structure. Okay, so you could use it in replacement of a B+3, for example. Okay, and it's again super fast. So here's the takeaway. A bitmap index supports both single and multidimensional data. Its greatest advantage is the ability to use bitwise operations. The disadvantage, obviously, is the long sequence of bits to be stored, but as I mentioned, there is a solution to this, which is to use advanced compression techniques to be able to manipulate the bits and the bit stream without having to expand the whole thing in one shot. In some database engines like Oracle, you could explicitly create a bitmap index. This is the syntax that Oracle uses. You would say create, and you put the keyword bitmap, and then the rest is what we have seen before. Index, give the index a name, and then you say on which table and in which column. Okay, so it's a very popular, super fast index that is considered a direct competitor to B+3s. Okay, you are still going to search, by the way, in the list of values to get the bitmap. Where if you remember in the previous example where we said, like, there was 30, 40, 50, okay, you still need to search. If you query select star from with value equal to 40, you still need to search for that 40. But here is the thing, you can put this in an extensible hash table, okay, or in a hash table, basically in a hash-based mechanism, in a hash-based index. So when you get select star from with value equal to 30, you can grab that from the hash index, and then the value for the hash index is going to be the bitmap that we have been discussing. Okay, so this is sometimes used in, along with hash-based indices to give you all of one access to the data, and it's also super fast because once you get the bitmaps, you can work with it. Magic on in terms of the bitwise operations you can do. These are the references for today's lecture. If you have any concern about the content, you should definitely consult the textbook.